Systems engineering is an interdisciplinary field of engineering that focuses on how to design and manage complex engineering systems over their life cycles. Issues such as reliability, logistics, coordination of different teams, evaluation measurements, and other disciplines become more difficult when dealing with large or complex projects. Systems engineering deals with work processes, optimization methods, and risk management tools in such projects. It overlaps technical and human-centered disciplines such as control engineering, industrial engineering, organizational studies, and project management. Systems engineering ensures that all likely aspects of a project or system are considered and integrated into a whole. History. The term systems engineering can be traced back to Bell Telephone Laboratories in the 1940s. The need to identify and manipulate the properties of a system as a whole, which in complex engineering projects may greatly differ from the sum of the parts properties, motivated various industries to apply the discipline. When it was no longer possible to rely on design evolution to improve upon a system and the existing tools were not sufficient to meet growing demands, new methods began to be developed that address the complexity directly. The continuing evolution of systems engineering comprises the development and identification of new methods and modeling techniques. These methods aid in better comprehension of engineering systems as they grow more complex. Popular tools that are often used in the systems engineering context were developed during these times, including USL, UML, QFD, and IDEFO. In 1990, a professional society for systems engineering, the National Council on Systems Engineering, was founded by representatives from a number of U.S. corporations and organizations. NCOSE was created to address the need for improvements in systems engineering practices and education. As a result of growing involvement from systems engineers outside of the U.S., the name of the organization was changed to the International Council on Systems Engineering in 1995. Schools in several countries offer graduate programs in systems engineering, and continuing education options are also available for practicing engineers. Concept: systems engineering signifies only an approach and, more recently, a discipline in engineering. The aim of education in systems engineering is to simply formalize the approach and in doing so, identify new methods and research opportunities similar to the way it occurs in other fields of engineering. As an approach, systems engineering is holistic and interdisciplinary in flavor. Origins and traditional scope. The traditional scope of engineering embraces the design, development, production and operation of physical systems, and systems engineering, as originally conceived, falls within this scope. Systems engineering, in the sense of the term, refers to the distinctive set of concepts, methodologies, organizational structures that have been developed to meet the challenges of engineering functional physical systems of unprecedented complexity. The Apollo program is a leading example of a systems engineering project. The use of the term system engineer has evolved over time to embrace a wider, more holistic concept of systems, and of engineering processes. This evolution of the definition has been a subject of ongoing controversy, and the term continues to apply to both the narrower and broader scope. Holistic view. Systems engineering focuses on analyzing and eliciting customer needs and required functionality early in the development cycle, documenting requirements, then proceeding with design synthesis and system validation while considering the complete problem, the system lifecycle. Oliver A.L. claimed that the systems engineering process can be decomposed into a systems engineering technical process and a systems engineering management process. Within Oliver's model, the goal of the management process is to organize the technical effort in the life cycle, while the technical process includes assessing available information, defining effectiveness measures, to create a behavior model, create a structure model, perform trade-off analysis, and create sequential build and test plan. Depending on their application, although there are several models that are used in the industry, all of them aim to identify the relation between the various stages mentioned above and incorporate feedback. Examples of such models include the waterfall model and the VEE model. Interdisciplinary field. system development often requires contribution from diverse technical disciplines. By providing a systems view of the development effort, systems engineering helps mold all the technical contributors into a unified team effort, forming a structured development process that proceeds from concept to production to operation and, in some cases, to termination and disposal. This perspective is often replicated in educational programs, in that systems engineering courses are taught by faculty from other engineering departments, which helps create an interdisciplinary environment. Managing complexity. The need for systems engineering arose with the increase in complexity of systems and projects, in turn exponentially increasing the possibility of component friction, and therefore the unreliability of the design. When speaking in this context, complexity incorporates not only engineering systems, but also the logical human organization of data. At the same time, a system can become more complex due to an increase in size as well as with an increase in the amount of data, variables, or the number of fields that are involved in the design. The International Space Station is an example of such a system. The development of smarter control algorithms, microprocessor design, and analysis of environmental systems also come within the purview of systems engineering. Systems engineering encourages the use of tools and methods to better comprehend and manage complexity in systems. Some examples of these tools can be seen here: system model, modeling, and simulation, system architecture, optimization, system dynamics, systems analysis, statistical analysis, reliability analysis, and decision-making. Taking an interdisciplinary approach to engineering systems is inherently complex since the behavior of and interaction among system components is not always immediately well defined or understood. Defining and characterizing such systems and subsystems and the interactions among them is one of the goals of systems engineering. In doing so, the gap that exists between informal requirements from users, operators, marketing organizations, and technical specifications is successfully bridged. Scope. One way to understand the motivation behind systems engineering is to see it as a method, or practice, to identify and improve common rules that exist within a wide variety of systems. Keeping this in mind, the principles of systems engineering are holism, emergent behavior, boundary, ALAA can be applied to any system, complex or otherwise, provided systems thinking is employed at all levels. Besides defense and aerospace, many information and technology-based companies, software development firms, and industries in the field of electronics and communications require systems engineers as part of their team. An analysis by the INCO's Systems Engineering Center of Excellence indicates that optimal effort spent on systems engineering is about 15 to 20% of the total project effort. At the same time, studies have shown that systems engineering essentially leads to reduction in costs among other benefits. However, no quantitative survey at a larger scale encompassing a wide variety of industries has been conducted until recently. Such studies are underway to determine the effectiveness and quantify the benefits of systems engineering. Systems engineering encourages the use of modeling and simulation to validate assumptions or theories on systems and the interactions within them. Use of methods that allow early detection of possible failures, in safety engineering, are integrated into the design process. At the same time, decisions made at the beginning of a project whose consequences are not clearly understood can have enormous implications later in the life of a system, and it is the task of the modern systems engineer to explore these issues and make critical decisions. No method guarantees today's decisions will still be valid when a system goes into service years or decades after first conceived. However, there are techniques that support the process of systems engineering. Examples include soft systems methodology, J. Wright Forrester's system dynamics method, and the unified modeling language all currently being explored, evaluated, and developed to support the engineering decision process. Education. Education in systems engineering is often seen as an extension to the regular engineering courses, reflecting the industry attitude that engineering students need a foundational background in one of the traditional engineering disciplines plus practical, real-world experience to be effective as systems engineers. Undergraduate university programs in systems engineering are rare. Typically, systems engineering is offered at the graduate level in combination with interdisciplinary study. INCOSE maintains a continuously updated directory of systems engineering academic programs worldwide. As of 2009, there are about 80 institutions in the United States that offer 165 undergraduate and graduate programs in systems engineering. Education in systems engineering can be taken as systems-centric or domain-centric. Systems-centric programs treat systems engineering as a separate discipline, and most of the courses are taught focusing on systems engineering principles and practice. Domain-centric programs offer systems engineering as an option that can be exercised with another major field in engineering. Both of these patterns strive to educate the systems engineer who is able to oversee interdisciplinary projects with the depth required of a core engineer. Systems engineering topics. Systems engineering tools are strategies, procedures, and techniques that aid in performing systems engineering on a project or product. The purpose of these tools vary from database management, graphical browsing, simulation, and reasoning, to document production, neutral import-export and more. System. There are many definitions of what a system is in the field of systems engineering. Below are a few authoritative definitions. ANSIEIA 632-1999, an aggregation of end products and enabling products to achieve a given purpose. DAU Systems Engineering Fundamentals, an integrated composite of people, products, and processes that provide a capability to satisfy a stated need or objective. IEEE-STD 1220-1998, a set or arrangement of elements and processes that are related and whose behavior satisfies customer operational needs and provides for life cycle sustainment of the products. ISO IEC 15288-2008, a combination of interacting elements organized to achieve one or more stated purposes. NASA Systems Engineering Handbook. 1. The combination of elements that function together to produce the capability to meet a need. The elements include all hardware, software, equipment, facilities, personnel, processes, and procedures needed for this purpose. The end product and enabling products that make up a system. INCOSE Systems Engineering Handbook, homogeneous entity that exhibits predefined behavior in the real world and is composed of heterogeneous parts that do not individually exhibit that behavior, and an integrated configuration of components and/or subsystems. INCOSE, a system is a construct or collection of different elements that together produce results not obtainable by the elements alone. The elements, or parts, can include people, hardware, software, facilities, policies, and documents. That is, all things required to produce systems-level results. The results include system-level qualities, properties, characteristics, functions, behavior and performance. The value added by the system as a whole, beyond that contributed independently by the parts, is primarily created by the relationship among the parts. That is, how they are interconnected. The systems engineering process, depending on their application, tools are used for various stages of the systems engineering process. Using models, models play important and diverse roles in systems engineering. A model can be defined in several ways, including an abstraction of reality designed to answer specific questions about the real world, an imitation, analog, or representation of a real-world process or structure. Or, a conceptual, mathematical, or physical tool to assist a decision-maker. Together, these definitions are broad enough to encompass physical engineering models used in the verification of a system design, as well as schematic models like a functional flow block diagram and mathematical models used in the trade study process. This section focuses on the last. The main reason for using mathematical models and diagrams in trade studies is to provide estimates of system effectiveness, performance or technical attributes, and cost from a set of known or estimable quantities. Typically, a collection of separate models is needed to provide all of these outcome variables. The heart of any mathematical model is a set of meaningful quantitative relationships among its inputs and outputs. These relationships can be as simple as adding up constituent quantities to obtain a total, or as complex as a set of differential equations describing the trajectory of a spacecraft in a gravitational field. Ideally, the relationships express causality, not just correlation. Tools for graphic representations. Initially, when the primary purpose of a systems engineer is to comprehend a complex problem, graphic representations of a system are used to communicate a system's functional and data requirements. Common graphical representations include functional flow block diagram, model-based design, for example Simulink, VisSim, etc. Data flow diagram, N2 chart, IDEFO diagram, use case diagram, sequence diagram, USL function maps and type maps. Enterprise architecture frameworks, like TOGAF, MODAF, Zachman frameworks etc. A graphical representation relates the various subsystems or parts of a system through functions, data, or interfaces. Any or each of the above methods are used in an industry based on its requirements. For instance, the N2 chart may be used where interfaces between systems is important. Part of the design phase is to create structural and behavioral models of the system. Once the requirements are understood, it is now the responsibility of a systems engineer to refine them, and to determine, along with other engineers, the best technology for a job. At this point, starting with a trade study, systems engineering encourages the use of weighted choices to determine the best option. A decision matrix, or Pew method, is one way to make this choice while considering all criteria that are important. The trade study in turn informs the design, which again affects graphic representations of the system. In an SE process, this stage represents the iterative step that is carried out until a feasible solution is found. A decision matrix is often populated using techniques such as statistical analysis, reliability analysis, system dynamics, and optimization methods. Other tools, systems modeling language, a modeling language used for systems engineering applications, supports the specification, analysis, design, verification and validation of a broad range of complex systems. Lifecycle modeling language is an open standard modeling language designed for systems engineering that supports the full life cycle, conceptual, utilization, support and retirement stages. Related fields and subfields. Many related fields may be considered tightly coupled to systems engineering. These areas have contributed to the development of systems engineering as a distinct entity. Cognitive systems engineering. Cognitive systems engineering is a specific approach to the description and analysis of human-machine systems or socio-technical systems. The three main themes of CSE are how humans cope with complexity, how work is accomplished by the use of artifacts, and how human-machine systems and socio-technical systems can be described as joint cognitive systems. CSE has since its beginning become a recognized scientific discipline, sometimes also referred to as cognitive engineering. The concept of a joint cognitive system has in particular become widely used as a way of understanding how complex socio-technical systems can be described with varying degrees of resolution. The more than 20 years of experience with CSE has been described extensively. Configuration management, like systems engineering, configuration management is practiced in the defense and aerospace industry as a broad systems-level practice. The field parallels the taskings of systems engineering. Where systems engineering deals with requirements development, allocation to development items and verification, configuration management deals with requirements capture, traceability to the development item, and audit of development item to ensure that it has achieved the desired functionality that systems engineering and/or test and verification engineering have proven out through objective testing. Control engineering and its design and implementation of control systems, used extensively in nearly every industry, is a large subfield of systems engineering. The cruise control on an automobile and the guidance system for a ballistic missile are two examples. Control systems theory is an active field of applied mathematics involving the investigation of solution spaces and the development of new methods for the analysis of the control process. Industrial engineering. Industrial engineering is a branch of engineering that concerns the development, improvement, implementation and evaluation of integrated systems of people, money, knowledge, information, equipment, energy, material and process. Industrial engineering draws upon the principles and methods of engineering analysis and synthesis, as well as mathematical, physical and social sciences together with the principles and methods of engineering analysis and design to specify, predict, and evaluate results obtained from such systems. Interface design. Interface design and its specification are concerned with assuring that the pieces of a system connect and interoperate with other parts of the system and with external systems as necessary. Interface design also includes assuring that system interfaces be able to accept new features, including mechanical, electrical and logical interfaces, including reserved wires, plug space, command codes and bits in communication protocols. This is known as extensibility. Human-computer interaction or human-machine interface is another aspect of interface design, and is a critical aspect of modern systems engineering. Systems engineering principles are applied in the design of network protocols for local area networks and wide area networks. Mechatronic engineering. Mechatronic engineering, like systems engineering, is a multidisciplinary field of engineering that uses dynamical systems modeling to express tangible constructs. In that regard it is almost indistinguishable from systems engineering, but what sets it apart is the focus on smaller details rather than larger generalizations and relationships. As such, both fields are distinguished by the scope of their projects rather than the methodology of their practice. Operations research. Operations research supports systems engineering. The tools of operations research are used in systems analysis, decision-making, and trade studies. Several schools teach SE courses within the operations research or industrial engineering department, highlighting the role systems engineering plays in complex projects. Operations research, briefly, is concerned with the optimization of a process under multiple constraints. Performance engineering. Performance engineering is the discipline of ensuring a system meets customer expectations for performance throughout its life. Performance is usually defined as the speed with which a certain operation is executed, or the capability of executing a number of such operations in a unit of time. Performance may be degraded when an operation's queue to execute is throttled by limited system capacity. For example, the performance of a packet-switched network is characterized by the end-to-end packet transit delay, or the number of packets switched in an hour. The design of high-performance systems uses analytical or simulation modeling, whereas the delivery of high-performance implementation involves thorough performance testing. Performance engineering relies heavily on statistics, queuing theory and probability theory for its tools and processes. Program management and project management. Program management has many similarities with systems engineering, but has broader-based origins than the engineering ones of systems engineering. Project management is also closely related to both program management and systems engineering. Proposal engineering. Proposal engineering is the application of scientific and mathematical principles to design, construct, and operate a cost-effective proposal development system. Basically, proposal engineering uses the systems engineering process to create a cost-effective proposal and increase the odds of a successful proposal. Reliability engineering. Reliability engineering is the discipline of ensuring a system meets customer expectations for reliability throughout its life. That is, it does not fail more frequently than expected. Reliability engineering applies to all aspects of the system. It is closely associated with maintainability, availability, and logistics engineering. Reliability engineering is always a critical component of safety engineering, as in failure modes and effects analysis and hazard fault tree analysis, and of security engineering. Risk management. Risk management, the practice of assessing and dealing with risk, is one of the interdisciplinary parts of systems engineering. In development, acquisition, or operational activities, the inclusion of risk in trade-off with cost, schedule, and performance features, involves the iterative complex configuration management of traceability and evaluation to the scheduling and requirements management across domains and for the system lifecycle that requires the interdisciplinary technical approach of systems engineering. Safety engineering. The techniques of safety engineering may be applied by non-specialist engineers in designing complex systems to minimize the probability of safety-critical failures. The system safety engineering function helps to identify safety hazards in emerging designs, and may assist with techniques to mitigate the effects of hazardous conditions that cannot be designed out of systems. Scheduling. Scheduling is one of the systems engineering support tools as a practicing item in assessing interdisciplinary concerns under configuration management. In particular, the direct relationship of resources, performance features, and risk to duration of a task or the dependency links among tasks and impacts across the system lifecycle are systems engineering concerns. Security engineering. Security engineering can be viewed as an interdisciplinary field that integrates the community of practice for control systems design, reliability, safety and systems engineering. It may involve such subspecialties as authentication of system users, system targets and others, people, objects and processes. Software engineering. From its beginnings, software engineering has helped shape modern systems engineering practice. The techniques used in the handling of complexes of large software-intensive systems has had a major effect on the shaping and reshaping of the tools, methods and processes of SE. See also: Enterprise Systems Engineering, Interdisciplinarity, List of production topics, List of systems engineers, List of types of systems engineering, Management cybernetics, Structured systems analysis and design method, System of systems engineering, Systems thinking, references. Further reading: Harold Chestnut, Systems Engineering Methods. Wiley, 1967. Harry H. Good, Robert E. Marshall System Engineering, An Introduction to the Design of Large-Scale Systems, McGraw-Hill, 1957. Derek Hitchens World-Class Systems Engineering at hitchens.net. NASA Systems Engineering Handbook. NASA SP 2007-6105 Rev 1, December 2007. NASA Systems Engineering Processes and Requirements 7123.1 billion Nepalese rupees, April 2013. NASA Procedural Requirements, David W. Oliver, Timothy P. Kelleher and James G. Keegan, Junior Engineering Complex Systems with Models and Objects. McGraw-Hill, 1997. Simon Ramo, Robin K. St. Clair, The Systems Approach, Fresh Solutions to Complex Problems Through Combining Science and Practical Common Sense, Anaheim, California, KNI, Incorporated, 1998. Andrew P. Sage, Systems Engineering. Wiley IEEE, 1992. ISBN 0-471-53639-3. Andrew P. Sage, Stephen R. Olson, Modeling and Simulation in Systems Engineering, 2001. Dale Sherman, Systems Cost Engineering, Gower Publishing, 2009, Robert Shishko al. NASA Systems Engineering Handbook. NASA Center for Aerospace Information, 2005. Richard Stevens, Peter Brook, Ken Jackson and Stuart Arnold. Systems Engineering, Coping with Complexity. Prentice Hall, 1998. U.S. 2D Systems Management College Systems Engineering Fundamentals. Defense Acquisition University Press, 2001, Malakuti, B. Operations and Production Systems with Multiple Objectives. John Wiley & Sons ISBN 978-1-118-58537-5. External links, INCO's homepage. 2D Systems Engineering ODASDSE site with reference materials, Systems Engineering Body of Knowledge Wiki, INCO's Tools Database, INCO's UK homepage, ICSEng homepage.